Mechanical vibration is the continuous exchange of energy within a physical system. It is the physical process of kinetic energy converting into potential energy, and then back again, over and over. When analyzing structural integrity, calculating static loads, how much dead weight a beam or a column can hold, is a necessary first step. But static calculations assume a perfectly still environment, and they fail to account for cyclical, repeating forces. Cyclical dynamic loads inflict microscopic damage. Repeated rhythmic flexing exploits tiny imperfections in a material, causing microscopic fissures to rapidly expand and spiderweb until the part eventually breaks. To predict how and when these failures will happen, engineers rely on a specific mathematical framework, a second-order linear differential equation. This is the universal equation of motion. It organizes any physical system into three interacting properties: mass, which dictates inertia; stiffness, which defines elasticity; and damping, which is the system's ability to dissipate energy. Preventing a structure from vibrating itself to pieces requires understanding exactly how these three variables balance against each other. To understand the math, we establish a theoretical baseline. We remove damping and external forces entirely, leaving a system governed by only two properties: mass and stiffness. Stripped down, the differential equation reads simply as mass times acceleration plus stiffness times displacement equals 0. Once set in motion, two opposing forces fight for control. The mass's inertia drives the block forward, while the spring's stiffness creates a restoring force that pulls it back. If we plot this continuous physical displacement over time on the right, the result is a perfect, unending sinusoidal wave. The exact timing of this cycle is called the natural frequency. Mathematically, it equals the square root of the stiffness divided by the mass. Because of this ratio, increasing the stiffness of the spring will shorten the wavelength and speed up the cycle. Conversely, adding mass increases inertia, which lengthens the wavelength and slows the cycle down. Every physical object, a guitar string, a steel beam, or a suspension bridge, possesses an inherent natural frequency. It is the structural heartbeat of the material itself. In reality, perfect endless oscillation is impossible. No physical system is completely frictionless, meaning energy will always dissipate into the environment. To model this, we reintegrate the damping variable back into the differential equation, representing it physically as a mechanical dashpot attached to the mass. The damper's function is to continuously remove kinetic energy from the moving system, usually by converting that motion into heat through friction or fluid resistance. As the damper bleeds energy from the system, the time domain graph changes. The perfect sine wave is compressed by an exponentially decaying envelope, shrinking the amplitude until the system comes to rest. Engineers quantify this rate of energy loss using a metric known as the damping ratio. The damping ratio dictates how the system settles. An underdamped system oscillates slowly to 0. A critically damped system returns to rest as fast as mathematically possible without oscillating. An overdamped system takes a sluggish, prolonged path back to its resting state. With mass, stiffness, and damping established, the system is prepared for the final variable, a continuous external harmonic force. We update the equation to its complete state by setting it equal to this external force, represented mathematically by a sine function fluctuating over time. Measuring the impact of forced vibration requires a different analytical tool. The time domain graph is discarded, and we shift our view to the frequency domain. This chart is a frequency response plot, often called a Bode plot. The vertical axis measures the magnification factor, how much the vibration amplifies. The horizontal axis measures the frequency ratio, the speed of the external force divided by the structure's own internal natural frequency. When the external force pulses much slower than the object's natural frequency, the ratio is less than 1. The object simply moves along with the push, and the magnification remains low. If the external force pulses much faster than the natural frequency, pushing the ratio well past 1, the mass's inertia actually isolates it from the rapid shaking, and the physical displacement drops near 0. But there is a critical failure zone in the middle. When the frequency of the external force exactly matches the internal natural frequency of the structure, the ratio equals precisely 1.0. The curve spikes violently. This precise mathematical alignment is called resonance. At resonance, the external force pushes the structure at the exact moment it already wants to move. The physical amplitude grows exponentially. With every single cycle, the vibration becomes completely unconstrained by the object's mass or stiffness. In a resonant state, the mass and stiffness equations cancel each other out entirely. The damping variable becomes the only physical constraint preventing the structure from vibrating to infinity. If a structure lacks sufficient damping materials to bleed off that energy, the physical displacement will rapidly exceed the material's structural limits. The entire discipline of vibration analysis exists to calculate exactly where this resonant peak will occur along the frequency spectrum, so that the system can be engineered to avoid it. Up to this point, we have modeled a single mass on a single spring. But real engineering structures are continuous physical bodies capable of infinite directions of movement. To handle this complexity, engineers divide these continuous bodies into a series of multiple masses connected by multiple springs. This is known as a multi-degree of freedom system. Because there are now multiple overlapping variables interacting at once, the single differential equation must be upgraded into a matrix format. The single mass variable expands into a comprehensive mass matrix, and the single stiffness variable expands into a corresponding stiffness matrix. This matrix format accounts for mathematical coupling. In a connected system, any movement in the first mass directly alters the tension on the springs attached to the second and third masses, creating chaotic feedback loops. The mathematical solution for untangling these coupled equations requires calculating two properties: eigenvalues and eigenvectors. Eigenvalues represent the multiple natural frequencies of the system. Unlike our simple single-mass model, a multi-degree of freedom system possesses several natural frequencies that exist simultaneously. Eigenvectors determine the mode shapes. These are the independent, predictable geometric patterns the structure will physically bend into when driven at each specific eigenvalue. By utilizing matrix algebra, engineers can mathematically decouple the chaotic physical shaking of a real-world object into a clean set of independent, predictable vibrational modes. We can apply this matrix theory to a practical engineering problem, like mounting a heavy, rotating industrial machine onto a structural frame. The first step in structural analysis is defining the external forcing frequencies. In this case, those forces are generated by the machine's operational RPM. The second step is evaluating the frame itself. Engineers build the specific mass and stiffness matrices for the design to calculate its inherent natural frequencies. Comparing the machine's operational frequencies against the frame's natural frequencies reveals exactly where dangerous resonance will occur. If found, the eigenvector maps the exact mode shape, showing how the structure will twist under that load. The primary intervention is rarely just packing the frame with damping materials to absorb excess energy. Instead, the optimal solution is to adjust the physical design to intentionally alter the mass matrix or the stiffness matrix. Stiffening a bracket increases K, while adding mass increases M. These adjustments shift the frequencies, safely out of operational range. This is the core methodology of researchers like Thompson and Dale. True structural integrity is achieved by mathematically predicting resonance long before manufacturing begins. By mastering these differential equations, engineers maintain precise control over kinetic energy. This ensures modern structures can safely absorb dynamic loads without failing.